Hey, Eray, thank you for the good talk. Although you may, without slides, it was a difficult thing to do. You can see me.
Yeah, I can.
Yeah, I'd like to make several remarks, and I think a little correction. The metric representation of quantum mechanical wave functions are usually infinite dimensional and not finitely dimensional.
But for finite quantum systems, they are. The entropy turns out to be...
The entropy is something else.
Yeah, the entropy turns out to be finite, actually. Even if you use the Hilbert space.
And I just enumerate the remarks, and then you can answer.
Of course. Just and feel free to shoot down whatever.
Using the universe as a reference machine is to express it that way is misleading in a couple of ways. Because, well, first of all, you kind of make a parallel between two different disciplines. I can imagine if you take a probability distribution in biology, say, not in physics, and show that it is computable, it doesn't mean that it is any way related to Solomonoff induction.
I don't get it. Can you? I didn't understand it.
Your argument goes like this, if I understand correctly.
Okay.
You take probability distribution that is expressed by the quantum mechanical wave function, and say that and show that it is computable. I agree with that, but it doesn't mean it's in any way related to Solomonoff induction, right? For that, you will need the quantum computer, the universal quantum computer.
Yeah, well, that's just theory.
Yeah, and then claiming that the universe is a reference machine. I mean, the reference machine computes something. The universe a priori does not necessarily compute anything.
Okay.
Right? And therefore, this parallel. I mean, you have to build a quantum computer in order for it to compute something.
Of course.
Just as you have in the classical sense.
So this should work for any machine that you can construct in the physical world. That's what I mean by that. But you don't use an abstract model. What this means is that you shouldn't use an abstract model of computation. And there is some nice discussion that I couldn't come to, but my talk wouldn't make much sense without explaining the convergence theorem first, because some of the audience isn't familiar with that. So it's actually elaborated a lot in that discussion section. Please read it.
I'm referring actually not to the convergence theorem, but to the invariance theorem. You obviously want to eliminate the degrees of freedom left by the invariance theorem.
That's true.
By postulating that the universe is this one reference machine, but you have to build the computer first, right? And
that's true.
Still the degrees of freedom, which computer you build, and then you have still the arbitrariness, which may leave you with a constant.
Okay, without wasting anyone's time, I'll try to answer as quickly as possible. Okay, why do we have this model of universal computer? To be able to simulate any other machine, right? But in the physical universe, you can already build particular computers. So I'm referring to the fact that you can build a particular computer, not a universal programmable computer in the physical universe. The universality comes from the fact that physical law supports universal computation. So it can be actually any quantum system. You do. No, you do. You just, okay, well, imagine that there is a volume, okay, spherical chicken. So within this volume, some computation occurs by any machine, any physical system, right? And it emits photons. And we have like detectors around this sphere. So the photons that are detected become the output of this physical computer. So this is a physical model of computation.
Yeah, but then somebody else could build a different...
Of course, it doesn't matter what computer there is in it. Okay, it doesn't matter which computer there is in it. It can be any computer, any device,
Sorry,
any physical machine.
Can I try to, whether I can help with a sentence or two?
Okay.
I think the idea is that the initial state of that volume of space-time are the bits that are fed into the universal machine. So that's like the input to the universal machine, and then what happens in that volume of space-time is like the particular Turing machine that these initial bits to the universal machine specify.
Exactly, and so just one thing, in recursive function theory, we don't quantify physical resources at all, not necessarily. So we are not quantifying time, space, energy complexity, or program size complexity at all. So I'm saying that using this abstract model of computation that does not accurately account the complexity, physical complexity of the computational device is inadequate for Solomonoff induction. And what would be the ultimate quantification? Measuring the physical resources precisely, like at the quantum level. So that's all I'm saying, actually.
Let's give other people.
Okay. He is a physicist. That's why he is confused. I'm kidding. I'm kidding. I'm kidding. Okay. But
Well,
please.
Yeah, this is a question for probably for all of you. I must say that I've been really confused by some recent papers, especially this paper by Leike about these bad optimality results and all that. So as far as I know, but this is a general question, so this is the start of the story, and I would like perhaps the panel can choose if it is only my, that is just that I'm only confused, or maybe the whole audience is confused about this. But as far as I know, the no free lunch theorems do not apply for sequential prediction in the terms that Solomonoff said with, well, Solomonoff induction, I would like to call it prediction, because instead it doesn't construct any hypothesis because it uses all of them, so it is not really a model, but just a weighting of all possible models. But in any case, that's a terminology thing, but it works quite well. We know that we have some kind of escape from that. But a different thing is when we go to interactive agents. So in some way, for some optimality criteria, it seems that some kind of no free lunch theorem could be applied to these. So we have these problems. So I think for AIXI, we could just argue that for some optimalities, we can find that any kind of agent is optimal. I think this is in one of these papers. So perhaps I have just misunderstood something, but this is exactly my confusion. And so at this point, can the panel answer the question, is there any theoretical agent, theoretical, I don't mean any practical agent, just theoretical agent, that at this point we can say that it is free from the no free lunch theorem stuff and all of that, or is it, for instance, these knowledge-seeking agents free from that, or can we say something about that?
Okay, there were a lot of questions in one. So first, there is some, for Solomonoff induction, there is some free lunch to be had. There was a paper by Tom Edward about that. Regarding the optimality criteria, so if you do Solomonoff induction, you're basically just doing learning. You're in this passive setting, and all you do is observe the incoming bits. And all the statistical literature will tell you, like, it will converge, it will predict the right thing. If you don't have the self-referentiality problems that Benja talked about. But even without this self-referentiality, if you're in a reactive setting like AIXI is, you're doing reinforcement learning, then you have the fundamental problem of reinforcement learning. You have to trade off between exploration and exploitation. And AIXI, by definition, strikes that trade-off in the base optimal way. You just do what Bayesian reasoning starting from your prior would tell you. And now you have this dependence on your prior, and in the passive setting, when you're doing sequence prediction, this bias goes away asymptotically. And in the reinforcement learning setting, it won't. Because the base optimal, if you act according to the base optimal way, you don't explore enough to actually lose all of that bias. And in the paper, we construct a bad prior such that the bias. It will basically, AIXI will never take any explorative action, and the bias will be retained, and you're stuck in this basically arbitrarily bad relief state. Okay, so now coming to the notions of optimality. So there's 3 notions of optimality that have been proven for AIXI. It's Pareto-optimality, balanced Pareto-optimality, and self-optimizing. The self-optimizing doesn't hold for the general class of commutable environments. And Pareto-optimality, we showed that, in fact, every policy is Pareto-optimal, so that's vacuous. Which leaves balanced Pareto-optimal, which basically just says, well, it does what AIXI does. Or if you believe in Leike intelligence, it says AIXI is the agent that has maximal intelligence. But that's only true if you're measuring intelligence with respect to the same universal Turing machine that you use to define AIXI. If you use a different machine, it can go as bad as. And that's why it would be really good to have a natural choice for a universal Turing machine. Maybe I should pass this on because I've been talking so long now. Do you want to comment?
Your answer is perfect. So.
Okay, any other questions? No? No.
Ouch.
It is somewhat related to the previous question, but I still do not understand why is the problem that AIXI doesn't do enough exploration, since it is like optimal in the senses we talked about.
So your question was, why doesn't it do enough exploration?
Why is that problem? So does it cause suboptimality? It doesn't cause suboptimality. So why isn't it's a problem that AIXI doesn't do enough exploration?
Well, it's not a problem if you have a good prior. But we currently don't know what a good prior would be.
I think it might be helpful to like have an example to sort of illustrate the point. If your real environment is like in each round you have one of 2 choices, and one gives you a small reward and one gives you a big reward. But in fact, this is like one of the things to your prior. But another thing that your prior assigns much higher probability is that the one thing gives you the small reward and the other thing gives you a huge penalty. Then if you have a discount factor, it can be the case that you always choose to get the small reward, and you never get this disconfirmed because you think it would be you would get this huge penalty if you ever press the other button, and in fact the other button would give you a reward. And so that's like the kind of thing where you have not enough exploration if you use the Bayesian prior and you like use the wrong prior. I don't know if that helps.
Any more comments? No? Any more questions? Okay, so it's 7 minutes to 12:30. That's how we say it in Dutch. So let's be back here at 1:30. And let's start at 1:30. So let's be back here at